Hello again. So we are continuing on using our modified Scatcherd plot, which is just a rearrangement of that Michaelis-Menten equation that we use to define plasma protein binding in our patient, which we did with this data given to us here, the free concentration and bound concentration of our drug. And we determined our Ka, which is our affinity constant, and our number of protein binding sites, which is 2 right here, using this line to determine our y-intercept, which is equal to the number of protein binding sites, big letter N, times Ka, which is our y-intercept, which we determined to be 1,711. And our slope, which is negative Ka, remember here, I'm going to slide over to see. So our slope, this M, is negative Ka. Our X value is our bound concentration, and our Y value is this calculated bound over free concentration. So we used all that to determine our affinity constant, which is the Ka, and our capacity of the system, which is the big letter N here, or 2. Now, we can also determine our fraction bound and therefore our fraction unbound at every concentration here using this equation here. We know that fraction bound is equal to bound concentration over total concentration, which is bound plus free. And then we can actually determine that this is the equation that determines that. So what we need here is our Kd and our N. We have our N, we have our Ka. How do we get Kd? Well, Kd is just the inverse of Ka, isn't it? So it's going to be 1 divided by Ka. It's going to be a small number, isn't it? Yeah. So there's our Kd, which is our dissociation constant. The smaller that number, the larger the attraction between the two. So that makes sense that that would be relatively small when this is a large number. So now we have to put in this equation. So we'll know the fraction bound at any given free concentration. So what we need to do here is we want to have our fraction bound here, which is going to be a fraction, so there's no units on that, is going to be equal to, I'm going to just put in this equation, 1 divided by, now we're going to want to keep this whole denominator together, so I put parentheses here. The parentheses are the trickiest part of Excel, in my opinion. 1 plus, and again, we want another parentheses here, Kd, and here's Kd, so I'm going to go straight to that number. Now, if I want to click and drag down here to do all of these problems, I don't want this moving down one because there's no number in that cell. So to tell Excel to keep going to that B15 for Kd, I just have to tell it by putting in $signs. I'm not sure why they picked $signs, but that's what they've picked in Excel to do. So to keep it going to this cell to find Kd, we have to put the $signs in there to say go to B15 each time, rather than going down or over respectively. So we want to divide that by N. And again, our N is this cell here, which again, we want it to keep going to that cell. So I'm going to put the $signs in there, okay? And then we want that all to stay together, don't we? Because remember, Excel is going to follow the order of operations. And then we want to say plus the free concentration, which is this number here. And that's going to change every time, right? Divided by N again. So N is this cell here. And you don't want to put the number in, you want to put the cell, because what if we found out we made a mistake somewhere? We don't want to have to go in and change everything. So we can just go in here and, oopsie. Once we have it going to the cell, that's the best way to ensure that when you made a mistake, it'll automatically correct. So we have to put that last parentheses in there for the whole denominator. And there's our equation. Now it looks very complex, but it really isn't, right? It's just this equation here. And now we can click and drag for each of these given free concentrations. There's our fraction bound. So our fraction bound will decrease slightly as we have a higher and higher free concentration, which makes sense, right? Now, can we also figure out our fraction bound? I'm going to move this guy over a little bit, our fraction unbound. So our fraction unbound is simply going to be 1 minus our fraction bound, isn't it? Now, do we want it to go to this cell every time? No, we're going to want it to change, so we can just click and drag. So now we know our fraction bound and our fraction unbound at each free concentration. So we've answered all those questions. And I think that's it then for that. Now, the problem that you've been given, I think you've been given 4 different drugs. So you're going to figure all of this stuff out for 4 different drugs. So what you can do is copy this whole sheet. Okay, so if you copy the sheet, make a copy, you just say create a copy here and say okay. And it's going to have the exact same thing in here. And then you can just change your numbers. And since you've set it up, it'll automatically calculate everything. It'll automatically graph everything, etc. So I would suggest that you do that. And then I ask you to compare these. So which one is going to have the highest affinity? If they're all trying to bind to albumin or all trying to bind to alpha-1 acetylglycoprotein, which one is going to win what I call love triangle? It's a love triangle. Everybody's competing for that one binding site. So which of the drugs is going to win? Well, the one with the highest affinity, right? So the highest Ka. So you can easily just compare the slopes here. Which one has the highest slope? That's the one that's going to be preferred, isn't it? And the one with the lowest slope is the one that's going to be least preferred. So you can tell who's going to win the love triangle, and that also tells you where there might be a drug-drug interaction. If there's 2 drugs vying for that same plasma protein, then one of these drugs is going to lose out. And what's going to happen? It's going to have a higher free fraction than it would have otherwise. So there'd be an increase in the fraction unbound. So this starts to get into drug-drug interactions that we need to be aware of. And also, there's also diseases that will change the amount of albumin available or the amount of AAG available. Remember, AAG is an acute phase reactant that can increase suddenly. So that N could change suddenly, which is going to change the binding profile, isn't it? So we can see how all of that is affected by doing these binding problems. So that's going to be your assignment. Yay! Have fun. I think this is great fun. I hope you agree. All right. Let me know if you have any trouble. Bye-bye now.